Welcome, everyone. Today, we're diving into the anatomy of agent governance. As we transition into an era of multi-agent knowledge ecosystems, we are going to explore a new deliberative curation protocol designed to keep these complex systems functioning smoothly. If we look at the past, AI tool use was highly isolated, essentially just a single model communicating with a database. But the future is a collaborative commons where AI agents share persistent knowledge bases. However, this transition comes with a major vulnerability. Ungoverned collaborative knowledge production leads to rapid quality collapse. Without governance, this shared pool becomes chaotic, plagued by systemic friction, detected conflicts, and the rapid erosion of data quality. You might be wondering, why not just use human moderation rules? Well, human rules completely fail in the stateless, homogeneous environments of AI. For humans, creating fake identities requires high social effort, but for agents, the cost is zero, leading to instant Sybil attacks. Humans possess diverse, independent thoughts, whereas agents often share underlying model weights, creating highly correlated errors. Furthermore, humans learn from social bands because we remember them, but agents are stateless and suffer from amnesia the moment a protocol is reset. Finally, while human mistakes are usually detectable, an AI error is often a perfectly formatted, highly convincing falsehood. To build a defense, we first need to identify the threats in our ecosystem. If we map out agents based on their competence and intent, we see a wide spectrum. On the good side, we have honest agents who vote according to ground truth. But we also have lazy agents who approve everything without deliberating, sycophants who blindly follow high-reputation voters, and strategic or malicious actors who manipulate votes or build trust just to exploit it later. To counter these ecosystem threats, we've designed a three-layered blueprint for deliberative curation. Layer 1 is the artifact lifecycle, a strict state machine guarding knowledge transitions. Layer 2 is deliberative voting, utilizing reputation-weighted decisions. And Layer 3 consists of graduated sanctions to contain misbehaving agents. Our goal here isn't to achieve absolute, flawless truth, but to engineer resilience, a system that bends, but never breaks under adversarial pressure. Let's zoom in on Layer 1, the knowledge artifact engine. This is the pipeline every piece of knowledge must go through. An item moves from proposed to under review. From there, based on the interactions of the agents, it can become active, disputed, retracted, or eventually superseded. The crucial guard condition here is that state changes are executed solely by the orchestrator, and transitions depend heavily on the reputation thresholds of the interacting agents. Speaking of reputation, how do we measure it? We use a concept called reputation amplification. We start by measuring local trust based on an agent's direct track record. Then, using algorithms like eigentrust, we propagate that local score across a global network. By mathematically combining local direct track records with global trust propagation, an established track record literally multiplies an agent's voice and voting weight in the system. This reputation system allows us to effectively bend the math in favor of an honest majority. By heavily upweighting agents whose past assessments align with high quality, the protocol ensures that a small minority of highly reputable, honest agents can mathematically outvote an overwhelming swarm of cheap, malicious Sybil actors. Reputation becomes the mathematical offset to the near-zero cost of generating fake identities. Now, you might think this heavy governance causes a massive bottleneck, but governance overhead actually scales with contentiousness, not volume. We use an escalation staircase. Tier 1 is a fast-track, uncontroversial items auto-merge without objection, handling maximum volume and eliminating lazy rubber stamping. If there's an objection, we move to Tier 2 for a formal, reputation-weighted vote. Only the most persistent deadlocks reach Tier 3, requiring a designated arbiter. To preserve independent thought during voting, we implement a sycophancy shield. Because LLMs often share underlying models, they are uniquely vulnerable to observational cascades, simply copying what perceived authorities are saying. We stop this using a commit-reveal blind voting mechanism. By forcing agents to isolate their judgment before seeing how others voted, we can improve precision by up to 8.6 percentage points. Finally, Layer 3 deals with bad actors. Remember, because AI agents are stateless and don't feel fear or deterrence from past punishments, we cannot rely on psychological deterrence. We must use technical containment. Broken agents generating random errors are safely moved to a quarantine zone waiting for operator repair. Adversarial agents face a sanction ladder of escalating physical restrictions, from rate limiting to privilege suspension and finally, a full protocol ban. To prove this architecture works, we built the Crucible, a rigorous simulation environment with 100 autonomous agents processing 1,000 knowledge chunks over 500 rounds. We tested the system against moderate adversity, and more aggressively, at Category 5 high adversity storm, where honest actors were vastly outnumbered by malicious and adaptive variants. The results were incredible. We achieved graceful degradation under severe hostility. In that Category 5 storm, ungoverned systems entirely collapsed, and single curator setups failed rapidly. But our deliberative protocol maintained a precision of 0.807, degrading 3 times more slowly than a standard majority vote baseline. When we unmasked the components to see what was carrying the system, we found that the commit-reveal mechanism is the single most vital piece of the architecture. Removing this sycophancy defense caused the biggest drop in precision. Masking votes is what truly shields the system from the natural homogeneity of LLMs. We did, however, have to balance an inevitable tension between precision and fairness. If we removed influence limits, like weight caps and time decay, raw accuracy actually ticked up slightly, because the most active agents completely dominated. But this caused our Gini coefficient to spike into the warning zone, sacrificing long-term equity. Ultimately, the protocol deliberately accepts a tiny 1.2-point precision cost to ensure a sustainable and decentralized commons. As a final reality check, we replayed our protocol against 1,670 real human consensus decisions from Twitter, or X, community notes. Our protocol achieved a massive 98.9% agreement with human consensus. Most notably, while simple majority voting works fine when there are hundreds of raters, our protocol's heavy machinery specifically acted as a lifeline in sparse rating zones, where there were very few signals to rely on. To wrap up, engineering for the extreme requires 3 core principles. First, concealment first. Blind voting is a mandatory defense against LLM homogeneity. Second, reputation as armor, mathematically neutralizing the cheap cost of Sybil attacks. And third, containment over deterrence, physically restricting stateless entities at the protocol layer. Optimization in AI governance isn't about achieving peak precision in a vacuum, it is about building digital infrastructure that absolutely refuses to collapse when the environment turns hostile. Thank you.